Hi, welcome to another lecture on Calculus 2. Today's topic is symmetries of polar graphs. Symmetry is a fundamental concept in art, architecture, and sciences with far-reaching consequences. So we are going to spend a little bit of extra time on this topic, definitely more than half a page that is allocated to it in the textbook. So here's the first example from architecture. This is the Sagrada Familia church in Barcelona, Spain. It's a work of a mathematician geometer, and you can see elements of geometry in all of his work, especially in this one. And case of symmetry is quite obvious here. You can see that the left and right are identical. How about other areas of life? Let's go take a look at some other pictures. Here's a picture of a model, and it's a reflected image in the y-axis. Now the quick question, which one is the true picture? How can we tell the true picture from its reflected image? Well, if there was a law of biology or anatomy that told us the beauty spot only forms on a certain side of the face, then we could easily say, well, one of these things is the true image and the other one is a reflection. But I don't know of such a law. But it's possible to figure out a way of telling a human face from its reflection, because the human face is not exactly 100% symmetric, and there could be some biological facts that helps us distinguish one from the other one. Definitely when it comes to the internal organs, left and right are not the same. It's one of the mysteries as to why our heart is on the left side, and pretty much all the single organs inside of our body have a definite location to themselves. Aside from that biological mystery that relates to handedness of the object, such a question arises in physics as well. Imagine instead of these two faces, one side was the image of the universe, and the other one was the reflected image of the universe in a mirror. Could we tell one from the other one, or would it be all looking identical? Of course, we are not meaning that we go and find a culturally familiar thing and tell one from the other. For example, if you look at the picture of your car, presumably the steering wheel is on the left side, and if you see on the picture that it's on the right side, then you know that's a reflected picture. But aside from those kind of trivial things, is there a way of telling the universe from its reflected image? This issue was very important in physics, and back in 1960s there were quite a bit of work on this, and some scientists showed that there are certain subatomic particles and interactions that are equivalent of violation of mirror symmetry, meaning the universe acts as if it prefers a beauty spot on one side of the face. So the image of the universe could be distinguished from the actual universe in that case. Aside from those exotic applications, there are many other cases where symmetry becomes crucial in the sciences. Let me go ahead and take a little tour here. This particular website is dedicated to the issue of symmetry in molecular compounds. You see on the left hand side there are about like 24 different kinds of symmetries mentioned, and for each of them many examples are mentioned. For example, this one shows up under pyramidal molecules, and this one I think is cyclohexane. So what is the concept of symmetry? Symmetry in the compounds is very important for study of the interaction of the molecules. So for example here, if we turn this object by a certain number of degrees, it goes and coincides with itself. So the concept of symmetry always involves some kind of a motion at the end of which the object appears not to have moved at all. So here let's go ahead and rotate this thing. So you notice that the object rotated, but at the end it is as if nothing has happened. An object can have various kind of symmetries. For example, this is a reflection symmetry now. They can have multiple reflection symmetries. And again, let's go back and take a look at the rotation symmetry of this. So those of you interested in chemistry might have dealing with this issue in your other classes. If you study crystals, they also exhibit a very large degree of all sort of symmetry associated with them. Also, if you take a course in abstract algebra, oddly enough, you are going to be dealing with a large number of symmetries. So the issue that we have in mind is the following. If I have a graph that is produced as a polar equation, can I tell the symmetries of that graph? Well, of course, if you graph it, then you can look at it and say, well, it is symmetric in such and such way. But the issue is, as a matter of algebra, can you tell the symmetry before you actually graph it? It's one of the basic topics. You have encountered that since perhaps even I would say algebra 1 back in middle school, and definitely in pre-calculus and calculus 1 the issue does come up. So let's go do a quick review of what this topic is about, how does it tie in with algebra, and then we come back. So how did we look at this issue in pre-calculus? We would be given an equation that involves x and y in it. So for example, you will have some function of x and y equal to 0. For example, y minus x squared equal to 0, which is more familiar to you as y equal to x squared. And then you ask yourself, if I graph this thing, would it have symmetry? Well, what do you mean by symmetry? Well, this is a familiar picture, so let's just quickly go ahead, take a look at that. So y equal to x squared is a vertical parabola, is that right? Vertical parabola is y equal to x squared. We say this is symmetric with respect to, so I'm going to abbreviate that because I'm using it quite often. Symmetric with respect to y-axis. What does that mean? It means if I take this picture and rotate it in space by 180 degrees, it will come on this side and coincide or overwrite or imprint on top of the left hand side. So if I pick a point here, and this point has coordinates x and y, if I rotate this thing in space, the net effect is that this is going to come to this point here. Well, what are the coordinates of that point right now? The coordinates of this point is minus x and y. From this we conclude that if you take an equation and replace, we are going to do replace x by minus x and replace y by just y, which means don't touch the y at all. If the resulting equation is equivalent to the original equation, so here I go do the replacement, I get y is equal to minus x squared. On the face of it, it looks different from that. But if you simplify, well, simplification here is very straightforward, just square this thing. What you get out of this thing is same equation that you had at the beginning. If they are if the equation after simplification becomes identical to what you had to begin with, then you have symmetry with respect to y-axis. If you had your function being x minus y squared equal to 0, or you might be familiar with x equal to y squared. What is that? That's the graph of a parabola that opens toward the right. So here, if you consider a point and rotate it in space around the x-axis, it will come and coincides on top of the this point below, which has the coordinate of y. This one up here has coordinate x and y. So this is y and this is x. Same x, but now we have minus y. So the transformation that we have here is that x, we leave it untouched, and y, we change it to minus y. We put it in the equation, becomes x is equal to minus y squared. On the face of it, this looks different from that, but of course if you square it, discrepancy goes away, and what you have here is same as what you had over there, and at the conclusion you say this picture is symmetric with respect to x-axis. Now, axis of symmetry doesn't have to be x or y axis. It's just for the sake of easy algebra. We are talking about them more often than others, but you could have had axis of symmetry just about anywhere. Finally, we have an axis, we have a type of symmetry that's called central symmetry, and this one, an example of it, let's write y minus x cubed equal to 0, or more familiar to you, y is equal to x cubed. What kind of a graph is this? Well, see this perhaps less often than that parabola, but it's not a big mystery either. It is looking like something like this. What kind of symmetry does this one have? In some sense, as a double symmetry, meaning if you take this thing, rotate around the y-axis once, and you get this, and take this and rotate it around the x-axis. So once around the y-axis and once around the x-axis, you come back to the curve that you had. What happened here, if I'm at the location x, y, once I go to left, I'm at the location minus xy. Once I come down, y also flips, becomes minus x minus y. Meaning both xy and minus x minus y are both on the graph of the equation that we have. Another way of coming to this spot directly is to go to the origin and go equal distance to the other side, but continuing and going to the other side. So if x is replaced by minus x and y is replaced by minus y, and the resulting equation is same as what we had before. So here, instead of y, I put minus y. Instead of x, I put minus x. I simplify. So this is on the face of it different looking than that, but if you multiply both sides by minus, you get y is equal to x cubed, which is same as what you had before. If your equation becomes equivalent to what it was, so equivalent means it's not identically the same, but after simplification it does become the same. You say you have symmetry with respect to the origin. Again, we could have studied symmetry with respect to any point, but it's a lot easier to talk about the origin, and we stay with that. Okay, this is a review of what you had in college algebra a few years ago. That was all there was to it, and it was very straightforward and sweet and everything. We want to do exactly same thing in polar coordinates, meaning our equation is not given in terms of the Cartesian coordinate x and y, rather it's given in terms of the polar coordinates. So if I'm given f of r and theta, so I have some combination of the radial distance and the angle theta. So you remember, if I have this point space, this distance is r and this angle is theta, I am giving a description of my curve in terms of these two. For example, I might say r minus cosine of theta equal to 0, or you are more commonly familiar with r being given in terms of theta. If such a curve is given to me, how do I find its symmetries? Well, of course, one easy way is graph it and look at it, but we are trying to understand it from point of view of algebra or trigonometry and calculus and so on. Without graphing, can we tell what kind of a symmetry it might be having? To understand this thing, well, we need to go back and be sure about our understanding on polar coordinates. Polar coordinates are a little bit fussier than Cartesian because a point has many representations. You remember we went through that issue last time. This is going to be a sticky issue here because, well, it's like having a person in a party and you want to introduce him to somebody else and he happens to have many nicknames and at any given point you don't know which nickname to use. So if I have this point, we said, well, we represent r and theta. Perhaps theta is measured between 0 and 2 pi. Perhaps in our mind r mostly positive and such. But it doesn't have to be like that, meaning once I arrive at this point, I can continue, go around the circle, and come back to this point, or I might decide to go the other way and come back to this point. So there are alternate representation of exact same point. Easiest way of doing that is just to go around the circle so many times. Each time you go around the circle, your angle is going to change by 2 pi. You can go 2 pi, 4 pi, 6 pi, or you can go the other way, minus 2 pi, minus 4 pi. So always an even multiple of pi. So I write 2n pi, 2n pi, yes, 2n pi. N will always be an integer, 0, 1, 2, 3, or minus 1, minus 2, minus 3, and so on. They are all fair game. And then we said, that's not the end of it. Unfortunately, there's even more. I could go into an angle of theta plus pi. So I could take my x-axis, turn it around. Let me draw it in some other color. So I say, suppose I turned my x-axis into this. So this is my now. So that was x-axis. This is my new x-axis. Let's call it x prime. On this axis, which is now opened by theta plus pi, I can back up to this point, meaning on this axis use a negative coordinate to back up on that. So here, let's negative side of that axis, let's put it on a dotted line. That's going to be minus r. So I could go theta in the pi, on that go to minus r, and I arrive at the same point. And again, I could go around the circle as many times as I want, so I can add the 2n pi to this one as well. So whatever coordinate we give, we can always attach a 2n pi to it. So what happened, to summarize, let's redraw this thing. How did I end up with that? Odd. Okay. So if I'm at the location r and theta, we always remember that theta is up to a 2n pi. You can go around the circle and come back to the same point. We need to go a little bit uphill to get used to following that I could come to this angle of theta plus pi. So this was, if this is theta, I add a pi to it, I come here, and this would be my new axis, and then I go the negative side, so that becomes minus r and theta plus pi. So I want to make sure everybody comfortable with this. So you go half a circle, and on this new location of the axis, you go to the negative side of that one. Negative side of that would be minus r and theta plus pi. Once you have that, then you can have add a 2n pi to it. So this pi plus 2n pi, you can summarize it at 2n plus 1 pi. So in short, this is going to be an even number, this is going to be odd number. So r and theta plus even multiplied pi, or minus r theta plus an odd multiplied pi. They're all referring to the same point. So a point has doubly infinite list of addresses. So worse than just having a few nicknames. It's like a very long list of nicknames, like 2 languages and so on, and they all refer to the same point. Now, why is that relevant to us? The relevancy of this thing is that we are trying to compare 2 points, and saying that if one of them is on our curve, then the other one has to be as well. The issue is if I focus my mind on this one and I want to get the other one, in Cartesian it was straightforward. It was just x and y, and this one was, well, minus x and y. There was no mystery to it. Each point had just one set of coordinates, and that was it. If this is this, and then this that. In the polar, the issue is that, well, one point on one side can be given in terms of one of these representations, and the reflection of it, maybe it's given with some other representation. You see, that's the difficulty. Okay, let's go ahead and practice this issue. So if I have, suppose I want to investigate reflection with respect to, so this is our y-axis. Since the word y doesn't show up there, sometimes they refer to it as the line theta equal to pi over 2. Either way, this is the x-axis, and sometimes, to divorce ourselves from Cartesian, we call this thing polar axis. Either way. So suppose I have this point here, and its sister point or symmetric point is on this side. Okay, so it's in Cartesian it was straightforward, xy minus xy. But here, if this is r theta, who is that? Well, easy. Let's go after the easiest. Easiest is, well, connect this thing to that. If these are same angles, this is theta, this is same theta. This angle is pi minus theta. Yeah, let's say this for the first round is same as that r. So this is r and pi minus theta. That looked painless enough. That r and theta on the right and r and pi minus theta on the left. Well, the problem is just that it's not necessarily all that simple. Sometimes you have to give all the other representations of this point as well. So what were all those other representations? For every point For every point we have all of these. So let's remember, r and theta, as you have, just add 2n pi to it. Or flip your r, theta, and odd multiple of pi added to it. So let's go ahead do this thing. So either I leave r intact, and whatever angle I have, I add 2n pi to it. The other option was flip the distance to negative minus r, take your angle, and add an odd multiple of pi to it. We had these two options. Well, let's go ahead and simplify. The first one becomes r, and 2n plus 1 pi minus theta, and the other option is minus r, 2n plus 1, and another one becomes 2n plus 2 pi minus theta. Now the only thing that is significant here is that this is odd and this is even. 2n or 2n plus 2 or 2n minus 2 is all the same because it's just a certain even multiple of pi. So let's go and perhaps so if I have my first point r and theta here, across the y-axis this guy can be any of the following. It could have been r plus comma odd multiple of pi minus theta, or I can have minus r, and again we said odd. Just to make a consistent notation, we said the only thing that is significant here is that this will be an even multiple of pi. It doesn't matter how you write that even multiple, so I just write 2n pi minus theta. Okay, let's go do a quick practice. So let me so here was the case of symmetry across the y-axis. So y-axis symmetry, or theta equal to pi over 2, involved checking the following. Let's start with an easy example. Now let's say show r is equal to sine of theta is symmetric with respect to y-axis. Okay, let's start with our easiest line of attack. Easiest line of attack is the following: r replaced by r and theta replaced by pi minus theta. If the new equation is equivalent to the old one, then you have symmetry with respect to y-axis. But r replaced by r means just leave it alone. Right hand side, replace theta by pi minus theta. Well, from trigonometry you need to know that sine of pi minus theta is indeed equal to sine theta. So this is some fact from trigonometry. I hope you remember that. Either do expansion or just remember the identity. So after this substitution, the resulting equation is equivalent to the original equation. That implies that you do have symmetry with respect to y-axis. Okay, now let's go to a more advanced setting. Suppose I want to show r is equal to sine of theta over 2 is symmetric with respect to, okay, show that this sine of theta over 2 is also symmetric with respect to y-axis. We might say, okay, if it is, let's try it. R to r and theta goes to the other side, becomes pi minus theta. So instead of r, I just write r. Sine of, instead of theta, I write pi minus theta divided by 2. Well, this is obvious. Sine of pi over 2 minus theta over 2. And again, you remember trig identity that this becomes cosine of theta over 2. Just apply the identity for some more difference of angles or just complementary angles. At any rate, what we get, obviously not equivalent to what was there before. That was sine, this is cosine. They don't have anything to do with each other. It's or at least it's not easy to tell. It's not easy to tell that this will produce the same graph as that one. So what conclusion do we draw? The conclusion we draw is that the test failed. We can't say anything. We don't say it doesn't have symmetry. We say test failed to say anything. Is that it? Well, no. We have all the other ones. That is, instead of pi, could have used 3 pi, 5 pi, 7 pi, and so on, but all of them will end up with the same cosine, which is not leading us to anything. Okay, none of them will succeed. So we go to the second batch of these addresses. Second batch says instead of r going to r goes to minus r, and theta goes to an even multiple of pi minus theta. The simplest of these would be r goes to minus r and theta also goes to minus theta. Let's convince ourselves that this is in fact a correct check before we actually do check it. So the original location is here. This is our r theta. Rotating to angle of minus theta means we are here. This is minus theta. Now on this axis, if I go to minus r, where am I going? Minus r will bring us back to this location. This is minus r minus theta, which is symmetrically positioned versus that one against the y-axis. So we made sure that r to minus r, theta to minus theta is in fact going across the y-axis. So now I go ahead and do this. Instead of r, I put minus r. Instead of theta, I put minus theta. Is this equation equivalent to what we had? Yes. Simply by remembering an identity that sine of minus theta is equal to minus sine of t. This is same as saying minus r is minus sine of theta over 2. Multiplying both sides by minus, I get the original equation that I had. So we showed that this thing is in fact symmetric with respect to the y-axis. Let's go practice this thing one more round. This is show r is equal to sine of well, Now I want to open the issue with respect to symmetry with respect to x-axis. Let's go ahead, write the criterion for it, and then we'll be ready to do that. So what I want to do next is to show that sine of theta over 2 is symmetric with respect to x-axis or polar axis. So well, let's go ahead and develop the criterion for it. The criterion is, well, if I have the location r theta and this is the x or polar axis, I want to know who is this. Who is this? Simple way to come to this location is, so okay, if this is for example 30 degrees, it's going to be minus 30 degrees. So this is the location r and minus theta. But by now we have learned a lesson that it's not sufficient to just have the most convenient address, but you have to have all the addresses. So what are the other addresses? One simple thing was to go full number of circles. So this is r and minus theta plus 2n pi. The other possibility is take this axis, turn it to go in this direction, turn it to pi minus theta, and then back up to location minus r. So I can have minus r pi minus theta, that is the base angle, plus any number of circles you want to go around. So to summarize, to check for symmetry with respect to x-axis, if your original point is r and theta, the point on the other side is one of these, either r minus theta plus 2n pi, or minus r, this is minus theta and then an odd multiple of pi, minus theta and 2n plus 1 pi. So we are doing it one by one slowly so we get used to this description. Okay, with that in mind, is this r equal to sine of theta over 2, is it symmetric with respect to x-axis? So I start with r is equal to sine of theta over 2. First line of attack is to replace r with r. So here I'm going to, instead of r I put r, instead of theta I put, let's start with just minus theta, see what happens. Sine of minus theta over 2 is the same as that. No, it isn't. So what do we say? So this test failed. Do we conclude that symmetry doesn't exist? No. You have to check every single one of these things and see what happens with all of them. You can't just judge based on one of them. So let's go test another one. Instead of r I put r. Instead of theta I put minus theta plus 2 pi. So what does my equation become? It becomes r is equal to sine of, instead of theta I have 2 pi minus theta over 2. I simplify this thing is sine of pi minus theta over 2. Again, we remember the identity that sine of pi minus t is same as sine of t. We need a good bit of trigonometry here. This actually does turn out to be sine of theta over 2. So we do have vindication that after substituting in this second round, after substituting with that, we see that we have symmetry with respect to x-axis. to get the better sense of this thing, let's try one more round. Suppose I want to ask you to show r is equal to sine of theta over 4 is symmetric with respect to x-axis. So we go try r to r and theta to minus theta. We already see minus survives here, and then this test fails. Next we try the other one, r to r, theta to minus theta plus 2 pi. What do I get? R is equal to sine of, I have 2 pi minus theta over 4. That is sine of, this is pi over 2 minus theta over 4. That is cosine of theta over 4. Well, this is sine, is cosine. We have no reason to say that these are equivalent or anything at this level. So this test also fails. What do you think is going to happen? We try next. R, same, theta minus theta plus 4 pi. So again, you remember we have to go through all of them. So r becomes is equal to sine of now 4 pi minus theta over 4. Now it looks like it's working because now it's pi minus theta over 4, and that is sine of theta over 4, and then now we are vindicated. So as to which one of these representations of a point are going to do the trick, it's from problem to problem is going to be different. For the most part, you have very first attempt is going to work up, but the bigger this denominator is, the more you have to go into the cases, and there's a connection here that perhaps you can employ. Okay, we tried two of these symmetries. How about symmetry number 3, symmetry with respect to the origin? So if I'm here at r and theta, who is diametrically opposite to me on the other side? One simple way to go at this point is r theta plus pi. That is, go an extra angle pi and just go distance r to that location. And of course, after you have gone here, you can go any number of full circles. That's going to be 2n circle, and then 1 here becomes any odd multiple of pi is going to be that location. Another one that you can say is that, okay, I come to this same angle of theta, but then I back up to this point. So I will come to angle theta, and then I back up to the location I want is minus theta. Well, what's a general form of that? Take that and add to it an even multiple of pi to represent just going around the circles. So these are the two basic ones that probably 90% of your problems are going to be answered by just testing these two, but expect perhaps somebody will throw a curveball, and then you have to try more of them to see which one is actually showing this kind of symmetry. Let's go ahead and test another example. Again, let's suppose I want to test r is equal to sine of theta over 2 show sine of theta over 2 is symmetric with respect to the origin, or we sometimes refer to this as the pole of the polar system. polar coordinates is just 0, 0. Okay, what do we do? Okay, let's see if we can cut through the step that are ahead of us and see what's going to work and what's not going to work, and let's put aside stuff that doesn't work so that we focus on things that are helpful. If I add an odd multiple of pi here, when I divide by 2, I end up converting my sine to cosine, just like we did before. So for example, if I try this one, see, r is equal to sine of theta plus pi over 2. This becomes sine of pi over 2 plus theta over 2. And that's going to be cosine of theta over 2. So those odd multiples divide by 2, convert my sine to cosine, and this becomes a dead end. I cannot go anywhere with it. So if there are any hopes, it's with the even multiple that are added. Let me try the first one. Does that work? Minus r is equal to sine of theta over 2. Okay, so I replace r with minus r, theta with just theta, and this is no go because, well, this is not equivalent to what I had before. This has a minus and that one doesn't. Let's try go up. Next, minus r is equal to sine of theta. The next even number is going to be, of course, 2 pi. This was 0 pi, 2 pi over 2. This is going to be sine of 2 pi over 2 is pi, pi plus theta over 2. Let's remind ourselves of the identity. Sine of pi plus t is minus sine of t. So this simplifies to minus sine of theta over 2. Minuses cancel each other out, and I get r is equal to sine of theta over 2, which is what I had at the beginning, and this is successful. So here we say test failed. Test failed means it's silent. It doesn't tell us yes or no or anything, just as maybe. This one also failed. This one succeeded. It's also, of course, possible that you test all of them and nothing is going to work. In that case, you say the symmetry is not there. So we went through examples that are a bit more substantial than what is usually covered, but it does take a bit of time to get used to polar coordinates because we are just so used to Cartesian. So let me summarize things for you. Okay, what are the checks to be done in general? We have 3 kinds of symmetry with respect to the polar axis, pole, or the y-axis. For each of them, there are 2 principal points to check. Here, 2 checks. Here are the 2 checks, and all the others you add a multiple of 2n pi to your angle. So at the beginning, f of r and theta is given to you. That's your equation, or r is given in terms of theta, whatever it is. Then you have to go and check. If you're checking for symmetry with respect to x-axis, check the first 2, but keep in mind that you might have to check a lot more. Again, if you're checking with respect to the pole, check the first 2. 99% of cases this is going to give you the answer, but in an advanced problem you might have to go dig deeper, add an even multiple of pi to your angle, and then check. If you are checking for symmetry with respect to y-axis, these are the first 2 principal points to check, or 2 representations of the points to check, and then additionally you might have to check even more. Okay, so again, we covered a bit more than the half a page that's allocated to this topic in your textbook. It deserves a bit more time, both in terms of how significant it is and also the complication that arises. So Keeping that in mind when you're doing the problems of this section, and hopefully you want to read more about symmetry. If you're interested in biology, an interesting question there is, why is our heart on the left hand side? What's the issue of left-handedness in issue of handedness in biology? If you are interested in chemistry, there's a word there to discover, like there are some sugars and there are mirror images of these sugars. One of them tastes sweet, or they are both taste sweet, but one of them gets absorbed, the other one doesn't. So important issues in chemistry, and of course fundamental issues in physics. They all tie to the issue of symmetry. Until next time, good luck and God bless.